Hi boys and girls, this is lecture 7.3, the topic, differential equations, growth and decay. This will be part 1 of our discussion. To solve a more general type of differential equation, a technique known as separation of variables must be used. This technique is to rewrite the equation so that each variable occurs on only one side of the equation. Notice here we have dy dx equals x over y. That's the differential equation. By cross-multiplying, we now have y with its differential dy and x with its differential dx. This gives us the equation y dy equals x dx. Let's use the separation of variables technique to solve these differential equations. For this first example, we'll multiply both sides of the equation by dx, which gives us dy is equal to x plus 2 dx. Now that the x terms are with the dx differential, we can integrate both sides of this equation. We'll end up with y is equal to 1/2 x squared plus 2x plus c, our general solution. In our second example, we'll cross-multiply. This will place y with its differential dy and 5x with its differential dx, resulting in this equation, y dy is equal to 5x dx. Now that the variables are separated, we can integrate each side of the equation. This results in 1/2 y squared equals 5/2 x squared plus c. When using the separation of variables technique to solve a differential equation, you don't have to put plus c on both sides of the equation. You can just put it on one side. I'm going to call this c1, and you'll see why in just a moment. I'm going to multiply this entire equation by 2 to eliminate the fractional coefficients. This gives me y squared equals 5x squared, but multiplying 2 times c1 just gives me another constant, which I'll now call c, since this will be the final form of the constant of integration. Now subtracting 5x squared over results in this equation. Y squared minus 5x squared is equal to c. In our third example, we're going to multiply both sides of the equation by dx, placing the differential dx with its variable x, and we're going to divide both sides of the equation by y, placing y under its differential dy. This results in dy over y is equal to x to the 1/2 dx. Now that the variables are separated, we can integrate both sides of the equation. This results in natural log of y is equal to 2/3 x to the 3/2 plus c sub 1. This is a temporary constant of integration, as it will undergo another change before its final state. We're going to solve for y by exponentiating both sides of this equation. This gives us y equals e to the 2/3 x to the 3/2 plus c sub 1. But the right side of this equation can be rewritten as e to the 2/3 x to the 3/2 times e to the c sub 1, but e to the c sub 1 is just another constant which can become the coefficient of this exponential equation, resulting in our final form y equals c e to the 2/3 x to the 3/2. Here we have a specific application of the exponential function, growth and decay models. When the rate of change of a function is proportional to the same function, the proportion can be written dy dt, which is the rate of change of the function, equals ky, the constant of proportionality, times the original function. The general solution to this differential equation is the exponential growth and decay model, y equals c e to the kt. Notice this general form contains two constants, c and k, which means that two initial conditions will be needed to solve for the specific solution. C is the initial value of the function y, and k is the proportionality constant. Exponential growth occurs when k is greater than 0, and exponential decay occurs when k is less than 0. Here we have a graph of the growth model y equals e to the x, where the coefficient of the exponent is positive and a graph of the decay model, y equals e to the negative x, where the coefficient of the exponent is negative. Here is the differential equation dy dt equals ky. The rate of change of y is proportional to y. The solution to this differential equation is the exponential growth or decay model y equals c e to the kt. But let's see how that solution is derived. First, we'll multiply both sides of the equation by dt and divide both sides of the equation by y, resulting in dy over y equals k dt. Now that the variables are separated, we can integrate both sides. Natural log of y is equal to kt plus c sub 1. Let's exponentiate both sides of the equation. Y equals e to the kt plus c sub 1, but as we saw previously, this right side can be written as e to the kt times e to the c sub 1. This is just another constant, which can become the coefficient of our exponential term, resulting in the final form of the equation, y equals c e to the kt, which is the exponential growth or decay model. In this example, we'll use two initial conditions to solve for a particular exponential growth model, then use that equation to find a specific value. We start with this statement: the rate of change of y is proportional to y, which is code for this differential equation. dy dt is equal to ky. Let's solve this equation. First, we'll multiply both sides of the equation by dt and divide both sides of the equation by y. dy over y is equal to k dt. Integrating both sides gives us natural log of y is equal to kt plus c sub 1. Exponentiating both sides gives me y equals e to the kt plus c sub 1, which, as we know, can be written as y equals c e to the kt. Now let's solve for c and for k. We'll start with the first initial condition, 0, 2. So putting 2 in for y and 0 in for t, we get that 2 is equal to c e to the 0, which means that c is equal to 2. And rewrite your equation with c filled in, y equals 2 e to the kt. Now let's use the second initial condition to solve for k. That was the ordered pair 2, 4. So when y is equal to 4, t is equal to 2. Let's divide both sides by 2. That means 2 is equal to e to the 2k. Take the natural log of both sides of this equation. You'll end up with natural log of 2 is equal to 2k, and dividing both sides by 2 gives us 1/2 natural log of 2 is k, and that's approximately 0.3466. So here's our specific exponential growth model. Y equals 2 e to the 0.3466 t. To solve for y when t equals 3, we'll have y equals 2e to the 0.3466 times 3. This results in a value of 5.657. That's it for today's lecture. And remember, exponential growth, it's as easy as 1, 2, 4. God bless you, boys and girls.